Hi, I welcome you to this session on Axial Flow Compressor. In the previous session, we discussed about the basics of efficiency, and we defined efficiency in terms of stagnation enthalpy and stagnation temperature. Now we also understood that ideal work is nothing but we can get if we know the temperature values at the inlet and at the exit. But the actual work you will get only if I know the velocity parameters, right? So in today's session, we will try to understand if there are any other parameters that will contribute for the work input that is required by the compressor blades. So let's begin. We will try to understand what happens to the axial velocity from the blade root to the blade tip, and then we get a clear idea about why there exists some loss in the work. So if I talk about the velocity distribution throughout the blade length, so at the hub section, if I assume that this is hub section, the velocity is not the maximum value, right? The velocity is maximum at the middle portion of the blade, and again at the tip the velocity gets reduced. Now when I say velocity, I am talking about the axial velocity, right? C1. If it is a rotor entry, it is C1. If it is a rotor exit, it is C2. So the point here is, at each and every point on the blade section, the absolute velocity of the air is not constant, it is changing, right? But when we defined velocity triangles, we defined only one velocity triangle, right? So what happens, how we finally arrive at one particular velocity when we have different velocities at different blade length, right? So the idea here is, if you can see the dotted line, right? Let me change the color. Yeah, if you can see the dotted line, so this is the magnitude of velocity at each and every point from root to the tip, right? So what we are going to do here is we will take the mean values of velocity for each blade row, right? So if you observe again carefully the last stage, the maximum velocity is again somewhere around 50% of the blade height, right? So it is not constant, it is changing from hub to the tip. So if I try to understand the velocity triangle for the same three cases, let's say for the hub, the mid portion and at the tip, I get the following velocity triangles. Let's try to understand this. So this dotted line represents the design value of axial velocity, right? So this is the value of C1 for which the rotor blades are designed, right? But, and this is a case where you can see somewhere in the, let's say, first half portion or second half portion of the blade, right? So what is the meaning of this? So when I talk about the axial velocity, that is the lower axial velocity, that happens either at the root or at the tip. So the triangle actually moves from point 1, that is the lower C1, to the higher C1 values, right? So from minimum axial velocity to the maximum velocity. Now this increased CA is due to the increase in C1, and that is happening at the midsection of the blade. And again the velocity triangle moves back to the initial value, right? So this is a cyclic process, right? So if I try to draw it in an X and Y axis, so let's say C1 begins somewhere lower from the root section, increases at the midsection, and again comes back to the lower values of velocity at the tip, right? So this is for one particular blade. If I try to represent it in terms of X and Y values, so this is how you get, right? So y-axis represents the value of axial flow velocity, and x-axis represents the blade length. Okay, so blade length means from hub to tip. Okay, so this is how the velocity triangles are changing with the change in the axial velocity, right? Similarly, the same change you can observe at the trailing edge. Although the values of C1 is being accelerated to C2, but the pattern remains the same, right? Again, the dotted line represents the design value of CA, and this second triangle, the bigger one, represents when the axial velocity is increased, and the smaller one represents that when axial velocity is less, right? So it's very interesting analysis. If you understand this, you will really enjoy aircraft propulsion, and in specific the jet engine analysis. So with this understanding, we can conclude that when you increase the axial velocity, the work absorbing capacity of the compressor blades will reduce. And similarly, if I decrease the axial velocity, the work absorbing capacity of the AFC will increase, right? Please note down these 2 points, very important from this analysis. So how we will try to address this reduction in work absorbing capacity is by a term called as work done factor. Now, what is this work done factor? If this work done factor is 1 or 100%, right? So then the work absorbing capacity of the compressor blades would be maximum, and that is represented by equation number 26. Now, because the axial velocity is not constant throughout the blade length, so we need to introduce a new parameter that is called as work done factor, which reduces the work absorbing capacity of the blades. This reduction in work absorbing capacity is being taken care by a term called as work done factor. Now, this work done factor contributes to the reduction in work absorbing capacity of the compressor blades. Now, first point, why this work done factor exists? Because the axial velocity is not constant throughout the blade length. It varies from the hub to the tip, right? So because of that, ohm exists, or the work done factor exists. Now also the work done for a compressor stage is represented by Cp del T of the stage, or in other words, I can solve for temperature change in a stage and convert it into W by Cp. Now, if I know the work required by the compressor, and Cp is the specific heat at constant pressure, right? And then if I solve for the temperature change and substitute the value of W, I get equation number 27, which tells the relationship between the temperature and the blade angles. Right? Similarly, I can, if Ca is assumed to be constant, I can change the blade angles into the air angles, right? So equation number 27 is very important, and it introduces a new term called as the work done factor into the temperature change. Now, so temperature change in a stage is represented by equation number 27. So in the next session, we will continue our discussion on degree of reaction of an axial flow compressor, right? So thank you.